All right. So, hello everyone. Welcome to this talk about common API security pitfalls. A disclaimer, I'm used to walking around when I present, but there's only like a meter here, so if I disappear, please come look for me next to the stage. So, lunch is at 12:50. We have 30 minutes to talk about API security, and then you can get some delicious food here at this great conference. When we talk about API security, let's set the scene. So we're going to talk about web applications. We're going to talk about an application being loaded from a server. In this case, it's an application to post some restaurant reviews. And essentially, when the application loads, it's going to contact an API. It's going to fetch some data. It's going to perform some operations against an API. And that's what we're going to talk about in this presentation. Of course, web applications, we all know that it's not only web applications anymore. Today, you have mobile applications, which are often also web applications, just packaged in kind of a mobile browser, an embedded browser, but that's essentially the gist of what we're going to talk about. Why this talk? Well, actually, this talk was kind of inspired by the OWASP Top 10 from 2017. You may remember that there was some kind of a controversy about that Top 10. We're not going to talk about that. But in one of the release candidates, they had an item, underprotected APIs. It was explicitly listed there as this is a major problem. Of course, one of the things you see here is that the vulnerabilities listed there aren't very API specific. Of course, they do appear in the API world, but they're reincarnations of previously existing vulnerabilities. So these things that we had before in traditional applications, we start seeing some version of that vulnerability in APIs as well. By the way, tomorrow there's a project presentation on an API security top 10. So they're actually deepening this whole API security topic within OWASP, so I highly recommend you go there as well. Before we get started about actual API security pitfalls, a small word about myself. I'm Philippe de RYCK. I'm from Belgium. There's a lot of stuff on this slide. You don't need to remember all of it. Just remember that I'm a trainer. So I teach developers how to build secure software. That's my main activity in my company called Pragmatic Web Security. And I'm also the organizer of a course in Belgium called SecOpDev. Everything is on this slide. Look it up during lunch. Talk to me during lunch. I'm a very friendly guy, so I don't mind talking to all of you over lunch. But you're here for API security, not for this stuff. So let's set the baseline. Let's set a basic point of where we're going to start. We're going to start by talking about German smartwatches. These smartwatches for children, you can put them on your kids and you can track where they are and see if they get home safely from school or whatever you want to do with your kids. But they had an API and security wasn't too good. It was so bad that Germany actually banned the use of these, or the sale of these smartwatches. They said, like, with all due respect, but we're dealing with kids here and the security is so bad, you're not allowed to sell this anymore. Usually, I don't like talking about companies that get it wrong because we all know it's hard to get it right. But what I want to talk about here is that a year later, so they got banned, they supposedly fixed their product, and a year later, researchers took another look at their APIs. And they discovered a parameter saying user grade with a numerical value. And it turns out if you change that numerical value to 1, you became admin. That's the baseline. We're going to start here. This is non-existing security. So first of all, you shouldn't be doing that. But we're going to talk about real issues on top of that. So we're going to start from this point on, and we're going to talk about certain things that you actually do get wrong in your APIs and you might want to pay attention to. One of the things I want to talk about first is referring to objects in your API. This is a story from T-Mobile where they had an API to consult your account details. And how they did that is you send a request to the backend and they gave you your account details. And how they refer to your account is with a phone number. Because they're a phone company and a phone number is kind of a unique identifier, so why not? Why not use that phone number to actually refer to the account? But they forgot to implement a proper authorization check. So if I knew your phone number and I substituted the phone number in the API call, I could get your account details. And that's obviously not something that you want happening in your APIs. And this happens in a lot of places. T-Mobile is on the slide here, but AT&T had the same problem, and Telefonica in Spain had the same problem. And that's a common vulnerability, and it's known as an insecure direct object reference. And essentially, the underlying problem is an authorization problem. You check many APIs, just like T-Mobile, check if the user is authenticated. But they forgot to check if you're actually supposed to access this particular object. And these things are unfortunately very common because APIs do work with identifiers. Here's an example of a tutorial I found online. It's building a RESTful API in 10 minutes. I can assure you in 10 minutes there's not going to be security in there. But that's, of course, also not the point of the tutorial. But this is how you get started. Like, oh yeah, this is a to-do application, of course, very simple example. And you get a function to read a task from that application. Very straightforward, very simple. You implement some delete features. You can see there's no authentication, no authorization, because that's not the point of the tutorial. So if you start building an API, you start with a proof of concept, and then you add authentication. And then you'll think about, oh yeah, I need to check if the user is authenticated, and you implement that. But unless you think about, hey, I also need to check if I'm reading or deleting a task, that the user is actually the owner of the task, or if you have a more complex permission model, that the user has access to that task through a shared environment or whatever, and that's where things get tricky. And unless you start, or unless you audit your code explicitly for these issues, you're very likely to miss them. And that's exactly what happened in the T-Mobile case and the Telefonica case and so many other examples out there. And these things really do happen, and they are really problematic. So the first pitfall is lack of proper authorization. You need to audit your code. Every endpoint or every entry point, you need to check what authorization checks do I need to enforce here. And that's a very hard problem to solve in real applications. By the way, the slides, you're free to take pictures as much as you want, but if you want a PDF of the slides, they're available online. On my Twitter account, you can find a link to the slides, and there's a lot more slides in there as well. Sometimes I do longer versions of the talk, so there's more pitfalls, but there's also content about some vulnerabilities and solutions there as well. Authorization. How do you do authorization? Well, to do authorization, you probably need to know who's making the call. So if you want to know who's making the call, very traditionally, if you have a client and a backend, you used to have a session. And a session, well, it's kind of very easy. You have this session object. You can know, okay, this is Philippe making the call. Yes, I want that or not. And sessions work very well if you have a small amount of clients and a small amount of servers. And this is a stateful system. It's probably not a REST API, because REST is kind of supposed to be stateless, but this is how we used to build applications. Of course, today, if you're building an API application, you're probably building something like this. You have a lot of clients, a lot of backend systems. You don't want state, you don't want sticky sessions or session replication, because that's, we don't like that. So we want a stateless system. However, I would argue that if you only have a limited number of clients, if you know upfront this is only for a couple of hundred users, it might not be worth switching the whole mechanism to a stateless mechanism. Because anyone who has implemented a stateless API knows it's not that easy to do. There's a lot of things you have to take into account, and a lot of things change because of that new paradigm. And this is something we understand very well. This is something that has some pitfalls, that some certain things you need to take into account. So I'm not saying that stateless APIs are bad or stateful APIs are good. I'm saying that there's a use case for both of them. And I don't see the benefit of switching to a whole new system just for the sake of making it stateless. If you don't need it, why go through the effort? Why switch something that your developers have understood for 15 years to something new where they might make mistakes that are not supposed to be there? So think about that. Switch to a stateless API for the right reasons. Of course, I'm also not recommending to write code that depends on the actual state, but keeping track of authorization or authentication information on the server is not that big of a violation of the statelessness. So if you want to show this in a picture, this is where you have your state in a traditional application. In your stateless API, you move this to the client. You're essentially pushing this to the client so you don't have to keep anything on the backend. You can spin up 1,000 more instances of that API and load balance the hell out of it just like you want to. Sure, you can do that. However, on a PowerPoint slide, this is easy to do. It's easy to move this to the client and we're done, right? Well, in reality, it's not that simple. In reality, this has a very, very big impact. Because now we're making authorization decisions with data kept on the client. Data the attacker can modify, data the attacker can tamper with. And that makes this a very dangerous pattern and requires us to take certain things into account. Most important thing here is integrity. You need to make sure that whatever you get back from the client has not been tampered with. Confidentiality also plays a role, but I'm not going to talk about that in detail here. How does integrity work? Well, chances are if you're moving towards keeping state on the client, you're using something called JWT, JOT, or JSON Web Tokens. This is what a JSON Web Token looks like. Well, in reality, you don't get the fancy colors. It's just a blob of data. But if you put this on this website, jot.io, you get this fancy color scheme. And a decomposition of the token. So this is the base64 representation, and these are the different parts split out into their respective elements. And you can see that the purple part, or the middle here, is the payload. This is the actual data. Very simple example here. In reality, the data is going to be a lot, there's going to be a lot more in there. That's essentially what's going on. And one of the good things about JOTS is that whenever you're using that, you're also, well, in 99.9% of cases, also using a signature. And the signature is there to protect integrity. The signature is generated over the header and the payload and will ensure, if you verify that when it comes back in, ensure that the token has not been tampered with. And if it has been tampered with, it will be rejected. If you write that code correctly. Here's an example of how to not do it correctly. So the APIs to do this, there are plenty of libraries supporting JOT operations, and many of them support functions like decode, which actually get you the data out of base64 without verifying the signature. What you should be doing instead is using the a bit more advanced parts of the API. You actually have an algorithm, you build a verifier, and then you actually verify the signature. But this is a very easy pitfall, because if a developer doesn't really know what the signature is supposed to do and doesn't really know the difference between decode and verify the signature, chances are that you make a mistake in your application. And again, this will work. The top code example, from a functional perspective, will work. And unless you write a unit test giving a fraudulent token with a real payload but a mismatch in the signature, unless you write that test, you will not detect this problem until somebody else detects it for you. And hopefully they report it and not exploit it, but that's kind of a big gamble to take. So this is, again, a pitfall, mishandling client-side session data. This is only one example. There's other examples where these things can go wrong as well. But this is something that makes this whole mechanism a bit more tricky. You need to understand what's happening here. By the way, JOTs also have support for encryption. So if you want to store confidential data in the JOT, which is already kind of a dangerous thing to do, you can encrypt the whole token before you send it to the browser. So if you're storing some sensitive thing there that might need some protection for privacy reasons, you definitely want to encrypt that as well. However, encryption is even more complex to set up. I'm not going to talk about that here, but if you have any questions, feel free to ask me. So back to our fancy JOT here. If you look closely, you can see in the signature part that we're using an HMAC. An HMAC uses as input the data and then a secret key. Of course, in reality, you don't call it super secret HMAC key. That's usually not a very good key to use, and you don't put it on PowerPoint slides either. So keep that in mind. But one of the properties of HMACs, here's how an HMAC works. And the properties are actually quite interesting. So what you get is you get the data, and you use an HMAC algorithm. Plenty of libraries have HMAC algorithms, and you give it the data and a secret key, and out comes this HMAC value, which you can ship to the client along with the data. Of course, the JOT library does all of this for you, but that's what happens under the hood. How do you use it? Well, whenever you get a data and a signature back from a client or another party, you can verify that. You can recalculate the HMAC using the data and the secret key, and out comes this value. And you can compare that to the actual signature. And if they match, if the signatures are the same, then you know that the inputs to the HMAC function were the same. And if they don't match, you know that something is wrong. You know that either the key has changed, which you have control over, so that's not going to be the case, so the data has changed somehow from here to here, so you just throw the token out. Very, very important, do not accept the token if the signature mismatches. Very interesting to see here, this is also known as a symmetric signature because you use the same key to generate signatures and to verify signatures. Very easy, right? You just define a string, or no, not a string, a value in a vault, you fetch that, and you can generate and verify tokens as much as you want. However, the moment you're building or sharing tokens with other applications or other services, this becomes a problem. Because if you generate a token and I want to verify it, I'm going to need your secret. Will you give your secret to me? Probably not. You're not supposed to either, because I'm very untrustworthy. No, seriously, if you start sharing this with other applications, it becomes a problem, because the moment somebody has a secret key, they can generate arbitrary tokens. So this use case for HMACs is very, very limited. It's single application use only. You have one application generating stuff and getting it back, sure, you can use this. But even the moment you're using 2 applications, sharing that secret among these applications is probably a recipe for disaster. Fortunately, JOTs support a second way of signing them. You can use an asymmetric signature. And here's how it works from a very high level. You have the data, and you have a signing algorithm like RSA, and you feed it a key, and out comes a signature. Very easy, very straightforward. This is what you send to the client, and what you get back whenever the JOT comes back in. And to verify this JOT, now we can use a verification function call. Libraries implement this as a generic function call, so you don't have to worry about the details, and you feed it a public key, and it gives you a Boolean result, true or false. If it's true, you know that the message is the same as the one that has been signed. And if it's false, you know that something has changed. This is actually a very interesting way of doing things, because now one service can generate signatures with a private key, and everybody else can verify them with a public key. These keys are known as private and public because the private one is the one you keep secret, and the public one is the one you distribute to everyone else. And this is how JOTs are, for example, used in OpenID Connect. If you choose login with Google, there's a lot of complicated OAuth stuff is going to happen, but in the end, the application is going to receive a JOT token generated by Google, signed with Google's private key, which you can verify with Google's public key. And that's a very powerful mechanism, and that is something that many people are not even aware of that is available in the whole JOT library ecosystem. So brings us to the pitfall. Don't misuse the signature scheme. HMACs are only useful within a single application. Even if you're building a microservice architecture with JOTs, it's recommended to use public-private keys, because that you know which service has generated one. You can verify the signatures with the public keys, and you're good to go. All right. Of course, we're talking about keys here. And if we're talking about keys, we're talking about crypto, and crypto is a very hard thing to get right. And one of the problems many people don't know about or overlook is key management. You're not supposed to use the same key over and over again. You need to rotate that key every once in a while. And if you rotate keys, that means you might have multiple keys in rotation, multiple keys being used. So how would you verify a signature if you have 5 keys? Like, try all 5 of them and see if one works. Well, probably not the best way of doing things. So what you need is you need a way to manage keys. You need a way to identify keys. And JOT, again, has a mechanism for that. So there are various mechanisms in JOT specifications to indicate what key has been used to sign a particular token. The simplest mechanism is the KID claim in the header. It stands for key identifier. So you can simply include a string-based value which points to a particular key. So let's say that you have an application using HMACs, and the application rotates its key every day. It could use a random identifier to identify these keys. Whenever a token comes in, it can read the header, say like, oh yeah, this was signed with key 17, fetch that proper key and verify the signature. Same thing happens or is possible with public-private keys. It's just a string-based identifier, so if you use that string to identify a key, you're good to go. There's more advanced mechanisms as well. If you, for example, want to do this in a distributed fashion, then you might want to use key URLs. So you can include a URL in the header saying, oh yeah, by the way, you can fetch my public keys from this particular location. That's a very powerful mechanism, allows dynamic configuration of keys, allows easy rotation without having to update your applications over and over again. Of course, what matters here is that you don't simply accept key URLs that point anywhere. Otherwise, I could give you a token and say like, oh yeah, you can fetch the keys from evil.example.com, and your application would load them. So no, you need to restrict where you load keys from, what keys you consider valid. But there is a mechanism to handle keys when you use JOTs. So it brings us here. If you don't think about this up front, you're going to have some trouble. This is something that is often overlooked or not even done at all. And that's definitely something that you need to think about up front. How will I manage that? What if a key gets compromised? How do I ensure that it's no longer considered to be valid in my applications? All right. So far we talked about keeping track of that authorization data, representing it, storing it on the client somewhat. But how do you get that back? How do you get the JOT from the client to the server? Well, in very traditional applications, we would use a cookie. A cookie with an identifier, and usually not 42, but a more long and random string. That's your secret identifier to point to a server-side session object. If you move to a stateless system, chances are you're using an authorization header with a bearer type and then your job token as the value here. This is the modern way of doing things. But this is often referred to as cookies versus tokens because this is a cookie and this is a token, but the comparison doesn't really make sense. Because why can't you put a JOT in a cookie or an ID in the authorization header? There's nothing preventing you from doing that. And this looks a bit crazy, like, oh, come on, nobody does that. What are you talking about? Well, honestly, we do. Because if you're using OAuth, and the client is calling an API with an access token, you're probably using the authorization header. If you're using a reference token, you're using this pattern. It's not 42, but it's a short identifier, pointing to some state on the authorization server. And if you're using a self-contained token, then you're using this type of authorization header. And what I'm going to talk about here is that, first of all, cookies versus tokens makes no sense. And it's actually cookies versus the authorization header, because cookies are a transport mechanism and a storage mechanism in the browser, and the authorization header is just as well a transport mechanism. But they have different properties, and they have a certain impact on your application. So let me put them next to each other to show you what the differences are and what the impact is. First of all, both headers can contain string-based data. Nobody prevents you from putting a JOT token in a cookie. Even though it seems silly, it's definitely possible. Cookies are designed to work well with a single domain. If you want to use the same cookie for different domains, forget about it. It's not going to work. The web is not supposed to work like that. The authorization header, you add that manually in your application. You can send it wherever you want. That's a benefit in some cases. However, cookies are handled automatically. For a cookie, you don't need to write a single line of code in the client. The browser will do everything for you, which is actually pretty cool. For the authorization header, you need to write code. You need to write code to fetch whatever you want to keep from a response from the server, store it somewhere in the browser, reattach it to outgoing requests. Code you write yourself is code where you can introduce vulnerabilities. That's unfortunately the reality. I don't want to go into detail on examples here, but these things do happen in practice. And then finally, and that's maybe the biggest selling point of cookies, cookies work well with the web. Cookies are always present. On any type of request leaving the browser, there will be a cookie. For example, if you're loading an image or a script from within the DOM, the browser will send a cookie if it has one. If you're opening a WebSocket connection, the browser will send a cookie if it has one. The authorization header, you can only add it on XHR calls. You can only make it or attach it to outgoing requests if you have control over the request. But if you do new WebSocket with the URL, you have no control. And the header will not be there. And I've had clients that implemented a system with the authorization header only to realize afterwards, like, oh crap, we have no information on these types of calls. And at that point, they were like, okay, how are we going to solve that? Well, let's make a complementary mechanism using cookies next to the authorization header so we have something for those. No. If you actually need those properties, think about these things up front and decide on a proper mechanism. And I know we all think cookies are dirty, and they kind of are. They need a lot of attention to make them secure, but they have some benefits in certain cases. So don't underestimate the impact of session transport. It has, in some cases, more impact than you might think, especially if you're dealing with cores and things like that. So keep that in mind for your applications. All right, that brings us to cores. APIs, requests, cross-origin requests are definitely not abnormal. The previous talk talked about some things coming out in the future to have better control, but for now we're dealing with cores. And with your APIs, what matters here is that you are certain that requests across origins are identified as cross-origin requests. And one of the ways to do that is to simply ensure you don't simply accept form submitted data. You always require a custom content type like JSON data or whatever your application is using. And when you do that, the browser will include an origin header on request. The browser will tell you like, hey, this request comes from a client-side context with origin https maliciousfood.com. And then you can make a decision, do I want to allow that or not? And your course policy is actually going to make that decision for you if you have a well-configured course policy. And this matters because there are applications that have a badly configured course policy and they are vulnerable to certain cross-origin requests that might steal information from that API. So you need to enforce a strict course policy. I know this is usually something that gets in the way as a developer, like why is the browser complaining? How can I get rid of these errors? But actually this security of your course policy really, really matters. There are plenty of vulnerabilities in these systems. One example is if you have to implement your own course library. So this is what you get from the client, an origin header. And today, many libraries and many frameworks have support for course, but course has been around for 7, 8 years, and 5 years ago, many frameworks did not have support. So people started writing their own solutions. Like, oh yeah, we can check if the origin starts with retrograde.com, that's probably fine, or ends with, or contains, or some dirty regex-based system. And that's probably not a good place to be in. Because if somebody sends you a request from this context, it's going to match against some of these filters. Or something like that will also match. This will match the ends with or the contains because retrograde.com is there at the end. So you need to be aware of these things. And these examples are, and if you start looking for this, there's plenty of talks about how course can be abused to steal Bitcoin currency from your wallet and stuff like that. Because many services are configured insecurely. Here's one example of how you can even screw it up further. This is something I found online when Googling for course policies of a product you can install on your server, and then you have to add this to your Apache config and you're good to go. Well, it will work, sure, but it might work a bit too good. Because what you're doing here is, I don't know if you can read Apache config or not, but what you're doing here is you're taking the value from the origin header, putting it into this value, and then echoing it back to the browser saying like, oh yeah, this origin is allowed to send requests to me. By itself, maybe not too bad, but the fact that you say, oh, and by the way, they can use whatever cookies that are stored there allows any cross-origin context to send requests to this backend from any, in the name of the user from within the user's browser. And this is bad, because course actually has a wildcard, the star, which you can use to allow any origin to send your request, but then you cannot allow credentials. So the combination of this is really, really dangerous. So if you have a course policy, you need to verify that you're not too relaxed, that you actually enforce a strict course policy, and that your implementation is actually handling these things correctly. I know this is only an overview. If you have questions, I'm available afterwards to give you more details, but of course these are pointers where you can dive deeper on these topics with very useful OWASP information and stuff like that. All right, so we talked about some advanced pitfalls. What about the basics? Why haven't I talked about basic things like input validation? What about this input? Should the API accept this, yes or no? Maybe, it depends. Here, probably not, because this is a numerical identifier, so it probably should reject string-based data that leads to SQL injection. But you kind of get the idea. Input validation matters. If you were in the previous talk from Katie, she talked about input validation as a defense in depth mechanism. Awesome. Lack of input validation is a pitfall. You need to have input validation. However, input validation alone can never be your primary defense. Input validation alone will not protect your applications. Input validation to me is good. It's very useful to keep the crazy things out. Data you know is invalid, just keep it out. You don't want that. But the moment your data becomes complex enough, input validation is never going to save you. Here's an example of an email address. Straightforward, right? No. Email address validation is a nightmare. Seriously, it's a freaking nightmare. And this email address is actually a valid email address. If you ask the RFC, they're like, yeah, sure, this is valid. But if you insert this in a SQL query, the way you shouldn't do it, it results in SQL injection. And this is valid data. And this shows you that input validation will never be a solid defense. If you know it's invalid, sure, you can keep it out. But even valid data can result in vulnerabilities later on in the API. By the way, you cannot mail me on this address because my email provider does think this is invalid and doesn't allow me to create that email address. Which, let's consider that a good thing. But the pitfall here is don't rely on input validation as your primary defense. It's supposed to be a first line of defense, but not the primary defense. You have to parameterize your queries or encode your data if you're dealing with HTML data and stuff like that. That brings me to another interesting point. Things are going to go wrong at one point in time. This is just history. We know this. Things will go wrong. So what do you do then? If something goes wrong in your public part of your application, does it affect every customer with a private account? Maybe, maybe not. And based on the cases that we see today, most often it does. A single vulnerability in maybe an unimportant part of the application has a huge impact on the rest because we don't compartmentalize. Why on earth was the admin API for the smartwatches the same API as the watches use? There's no point in doing that. Split it out. Make it two completely separate things so that if something goes wrong in the watch API, at least it doesn't give automatic admin access. And this is something, in my opinion, this is the only way forward if we start compartmentalizing things. There's no point in building one huge API using the same authorization mechanism everywhere because if you have one failure, it's going to affect everything that you're doing. So if you want to take away one thing from this presentation, make it this. Or whatever you want, but I recommend to use this. So to wrap it up, I want to ask you to question everything. Don't just do things because somebody says that's the way to do this. Don't assume that everything I said here needs to be implemented the way I say because